Hello. We are going to talk about the future of genetic screening for premature ovarian failure, or POF. From this moment, we will refer mainly about POF. My name is Carlos Trujillo. I am a medical geneticist working in INSER. Premature ovarian failure has been defined as menopause before the age of 40, with elevated LH and FSH and low levels of estrogens. The age of menopause is a heritable trait and is considered now to be a polygenic, meaning that there are many genes that act together to produce this phenotype. The heritability of menopause from mother to daughter pairs range in different studies from 44 to 65%. The identification of the genetic causes of in POF is useful not only for the patient, but for the close female relatives, because cryopreservation of eggs or ovarian tissue or embryos is a possibility that we should take advantage of. The genetic causes of POF are diverse. We have karyotypic or chromosomal abnormalities, single gene defects, no coding RNAs, mitochondrial gene defects, and polygenic causes. Among the single gene defects, there are some autosomal defects that are syndromic, like galactosemia, and others. Isolated disease, non-syndromic, like, for example, FSH or LH resistant due to mutations in the receptor. Immune function genes like interleukin 11. Some DNA repair genes variants, like, for example, the one associated with microsatellite instability, MSH4, MSH5, and some of the Fanconi anemia genes that are also associated with some cancers like breast cancer and ovarian cancer. Premature aging syndromes like Bloom syndrome and Werner syndrome, and so do Werner syndrome due to MDM2 mutation that we recently reported in 2017, a dysfunction of this MDM2, which controls normally the P53, which is a tumor suppression gene, and usually in cancer is decreased. In this patient with premature aging is overactive and is producing the aging. And also in the females affected with this syndrome, there is a premature ovarian failure and usually menopause before the age of 18. X chromosome defects, abnormalities are cause of more than 12% of the cases of POF, are either whole or partial deletion, duplication, or translocation of the X chromosome. The most common ones are the X monosomy, 45X, or Turner syndrome, which has an incidence of 1 in 2,500 births, female births, and is associated with short stature, gonadal dysgenesis, and primary amenorrhea. Trisomy X, or 47XXX, is more common, occurs in 1,000 females. Usually the phenotype of these females is normal, and very often is present as a mosaic with other cell lines like 45X, quadruple X, 48XXXX, or a normal cell line as a mosaic with the triple X. They are easily detected by the regular karyotype or by FISH. In the chromosome X, we have in the long arm of the chromosome X, there is two regions called POF1 and POF2, which are critical regions, and they are associated with abnormal structural variants of the X chromosome that causes POF. No single gene has been found in this region, but genes for normal ovarian function for sure are in this area. Here we see a balanced translocation between the long arm of chromosome 9 and the long arm of chromosome X that cause POF. Also duplication in the long arm of the chromosome X or deletions in the long arm of the chromosome X are causes of POF. The most common single gene defect associated with POF is the Fragile X associated primary ovarian failure. Usually, the patient have a pre-mutation that is carried in 1 in 250 women. The normal gene, the FMR1, has 45 repetitions, less than 45 repetitions of a triplet, with this cytosine, guanine, and guanine, and guanine. And when there is a pre-mutation, this repetition is amplified from 55 to 200 times, and it increases the risk of POF. And the highest risk is when this amplification is between 80 and 100. Above 100, the risk is also high, but not as high as in this range. FMR1 permutation is the main heritable cause of sporadic and familial POF. 20% of the women who carry a Fragile X permutation develop POF, compared with only 1% of the population. But if the permutation is from 80 to 100, the risk is 40%. 1% of the women will have menopause before the age of 18 when they carry a permutation. Age of the menopause is 5 years younger than the average of the general population in these permutation affected persons. When there is a permutation, the risk of a full mutation of more than 200 repeats in the next generation increases according to the number of repeats in the permutation. When the permutation is above 100, the risk is close to 100 to have in the next generation the full mutation, which will present with the full-blown syndrome as the Fragile X syndrome that is associated with sometimes with severe mental retardation or intellectual disability. Recently, studies of the whole exome from the more than 135,000 patients from the UK Biobank found rare variants in genes associated with menopause. In these 3 genes, they found association with early menopause, and in these 4 genes, association with later menopause. The CHEK2 gene is a tumor suppressor gene, which has been associated also with uterine fibroids, polycystic ovarian syndrome, prostatic hypertrophy, and breast cancer risk. Usually, the normal CHEK2 destroy the eggs when they have damage of the DNA. But when it's lacking the CHEK2, these patients have a delay in the menopause of more than 3 years. And they respond strongly to the ovulation of IVF. There is another gene similar to this that is called CHEK1 that also is considered to be a tumor suppressor gene, but no homozygous loss of function in human tumor has been detected yet. When there is a CHEK1 inactivation, this is associated with infertility, but when there are extra normal copies of the CHEK1, it's also associated with longer reproductive potential and later menopause. Also, a recent study published in Nature Medicine in July 2023 evaluate most of the genes causal homologenic disorders or POF using exomes from more than 200,000 patients from the UK Biobank. Half of these genes are autosomal dominant, and they found in this study that they are either partially penetrant or no pathogenic at all. Curiously, these genes are used in panels that are commercially available, and of course, after this study, it doesn't make any sense to use these panels anymore. So, in conclusion, in this study, they found that most of the cases are probably due to multifactorial or polygenic reasons. Almost all traits and common disease are multifactorial or polygenic. The difference between multifactorial and polygenic is that the polygenic plus some kind of environmental trigger produce is what is called multifactorial. The genetic diseases are usually classified as monogenic or polygenic. Monogenic are due to a single variant or a single mutation that produce the disease. Like typical examples of this, we have the cystic fibrosis, the hemophilia, and Duchenne muscular dystrophy. But most of the diseases of the adult and the children are due to polygenic reasons. Like, for example, in ischemic heart disease, there are many variants that sometimes are more than 100 of variants or mutations that produce the disease. These variants, when they are due to only a change of one nucleotide, we call them SNPs, or single nucleotide polymorphism. When we do a whole genome sequencing of a person, we find more than 5 million of these SNPs or variants. But in the whole population, these variants are present in more than 100 million variants or SNPs. When we filter and we select only the variants that are inside of the genes, we can reduce this number of variants to around 22,000. And if these 22,000, probably there will be only hundreds of them who are really deleterious, and few of them will be casual variants or monogenic diseases. And these variants have been associated with different phenotypes, different diseases, and for example, with poor ovarian response, we have found variants or SNPs in the FSH and LH and estrogen receptors, and they are diagnostic markers of poor ovarian response. Also, in the anti-Mullerian hormone AMH receptor, there are SNPs that they are increase the risk of diminishing ovarian response. Also, SNPs in the p53 tumor suppression gene have been shown to have an impact in the results of the IVF. The polygenic model has been described in genetics for more than a century, it was described by Ronald Fisher, and it states that a trait is influenced by infinite number of SNPs. At that moment, he called it genes. So as we see here, as the number of SNPs or genes increase, there is a moment that there is a threshold where the phenotype of the disease is clearly manifest. Also, environmental factors may trigger this disease or this trait, and also reduce the number of SNPs that then is needed to produce the disease by displacing the threshold to the left. But there are so many continuous traits where there is no threshold. For example, in the skin color, there is a gradual number of SNPs that increase and is associated with the color of the skin. And this also is valid for the blood pressure, for the height, for the intelligence, and for the age of the menopause. The association of SNPs with diseases has been found through case and control studies called GWAS studies, which have been developed mainly in the last 20 years. Basically, a GWAS is a case and control study where we have hundreds of thousands of patients, and we have also thousands or millions of persons who are controls. And in each one of those, we evaluate a series of SNPs, which could be from around 500,000 to more than 5 million SNPs. Here we see, in this graphic, we see only 3 SNPs. The first one and the second one there is no difference between the cases and the controls, but in the third one, we clearly see that the SNP number 3 is associated with the disease compared to the controls. 3 factors enabled the development of GWAS during the last 20 years. One was the establishment of biobanks like the UK Biobank, which has a collection of more than 500,000 persons, which have been clearly, carefully phenotyped and also genotyped, and there is sequence of many, whole genome sequence of many of these patients and exomes. The second one is the HAPMap project, which was started in 2003 after the completion of the Human Genome Project, and it lasted for 3 years until 2006. In this HAPMap project, the There was a catalog of SNPs in different populations from all over the world, and is enormously useful for these studies of GWAS and extremely important. And the third one is the technological advances that develop the microarrays that now allow to study millions of SNPs in a single patient at the time, with prices that are very accessible now for these studies. From GWAS, we develop a way to score the SNPs that is called polygenic risk scores, or PRS. A PRS is a number that summarizes the effect of the genetic variants on an individual's risk of developing a disease. Each SNP is given a weight and according to its association with the disease. The addition of these weights gives the PRS, or the final number. The higher the PRS, the higher the risk of the disease. Here we see in a big study of thousands of patients with cardiovascular disease, where they evaluated more than 6 million of SNPs. They found that more than 95 SNPs of gene regions were associated with the myocardial infarction. And they developed a prediction using PRS and using machine learning and artificial intelligence. This PRS is now used in clinics all over the US, in cardiology clinics, and is an independent risk factor, independent of the values of cholesterol, triglycerides, independent of the family history, independent of the smoking history, and is even stronger than all these risk factors. But also for other diseases like atrial fibrillation, diabetes type 2, and breast cancer, there has been PRS that are now starting to be in use. For example, for breast cancer prediction, and in 95% of the breast cancers who are no inherited, we call it sporadic or multifactorial or polygenic, and we can stratify the risk according. If the patient has a low risk, maybe there is no need for screening, or the mammography can be due, every 3 or 4 or 5 years. But if the patient has a high risk, the screening by mammography should start at 30 years of age, and maybe also MRI should be used in the screening of these patients. Because if a patient has a PRS above the 90 percentile, the probability of developing breast cancer is about 33%. And if the patient PRS is above the 95 percentile, there is a more than 50% probability of developing breast cancer. And this is equal or similar to some of the heritable breast and ovarian cancers like BRCA1, BRCA2, PALB2, CHEK2, ATM, RAD51, and others. In the field of the age of menopause, also there has been several GWAS done in the last 15 years. The first one reported in 2012. They evaluated less than 20,000 patients, and they found 13 regions associated with or 13 SNPs associated with the age of menopause. Later, in around 2020, there was another study with close to 50,000 patients, where they found 49 regions. And the latest is a big study done with the exomes of the UK Biobank, more than 200,000 samples. They found 290 regions or SNPs associated with the age of menopause. So in this study, in the last study was mentioned, it was possible, for example, to detect the high risk in the top 1% or above the 99 percentile of the PRS score. The patient have an increased risk of 5 times above the general population, and this is the risk similar or equivalent to a patient who have FMR1 gene permutation. So, in conclusion, genetic variation could help predict timing of the menopause. Very soon, all these tests will be available to make these predictions, and it will be help in planning ahead, preserving oocytes, ovarian tissue, or embryos, not just for the patient, but also for the close relatives who can be evaluated using this PRS. It will be possible also in the near future to extend fertility by use of CRISPR and gene editing. And these technologies are now applicable in other fields, like, for example, in hematology, there are many cases of correction now of sickle cell anemia using these technologies, and for sure will be available in other specialties. Thank you very much.